Hi, my name is Manan Garg. I did my summer of science on quantum mechanics and this is my end term report video. So today I will be discussing the postulates of quantum mechanics in the language of Dirac notation. Then I will also delve into the uncertainty principle. The first postulate describes the state vector psi. It says that the complete information about the state of a quantum system at any time t is contained in a state vector psi of t. Psi of t belongs in an infinite dimensional complex vector space, that is a Hilbert space. The normalization condition tells us that we can visualize psi of t to lie on a unit sphere in the infinite dimensional vector space. The second postulate tells us that to every physically measurable quantity q called an observable, there corresponds a Hermitian operator q. Just a recap, all Hermitian operators are normal operators, which means that they have a set of eigenvectors which forms a complete and orthonormal basis for the infinite dimensional vector space. The third postulate tells us that whenever a measurement on the observable q is made on the quantum system in state psi, the only possible outcomes of the measurement are the eigenvalues of the operator q. Further, the effect of making the measurement is to instantaneously collapse the state of the system from its initial state psi to the corresponding eigenstate psi n after the measurement. The next postulate, often called the generalized statistical interpretation, tells us the probability of getting different outcomes, different eigenvalues as the outcomes of measurements. So it tells us that the probability of getting particular eigenvalue qn as the outcome is equal to the square of the component of psi along the eigenstate psi n. We can come up with the explicit expression for the probability as given in the slide. It is a fun exercise in Dirac notation to derive the expression for the expectation value of an observable q for a quantum system in the state psi. So let us do that. We know from the generalized statistical interpretation that upon making a measurement of the operator q, the probability of getting the outcome qn is given by this, where psi is normalized. So we can calculate the expectation value using this formula. Substituting this into this, we get we can write the norm squared as now using the conjugate exchange symmetry of the inner product, we can further simplify this as notice that the state vector psi is independent of n, so we can take this out of the summation sign. Now note that psi n is an eigenvector of the operator q, which means that it obeys this equation. Utilizing this equation, we can simply simplify this too. Again, the operator q is independent of n, so we can take that out of the summation. Note that this term is simply the resolution of the identity and it is equal to the identity, so we can simply say, and this is the final expression for the expectation value of the operator Q. The fifth postulate describes the time evolution of the state vector psi. So the state vector evolves in time according to the Schrodinger equation. Note that the Schrodinger equation is a first order differential equation in time, which means that it only needs one boundary condition in order to find the entire solution. Basically, this means that if we know the state of the system psi at any time t0, then we can determine the state at all other times. The uncertainty of an observable Q in the state psi is defined by this formula. Let us try to get an intuitive feel for what uncertainty really is. Going back to the unit sphere picture, suppose this is the true state vector psi, and psi n is an eigenvector of the system. If psi is really close to psi n, then it would have a high component along psi n, which would mean that the probability of measuring Qn, the eigenvalue corresponding to psi n, would be very high. In that case, the probability density curve may look something like this, where there is a high probability of measuring Qn and low probability for all other outcomes. On the other hand, if psi is really far from psi n, in that case it would have a small component along psi n and the probability density may look something like this. It is clear that the standard deviation in this curve is much smaller and in this curve it is much larger. However, we have more confidence in our measurement of Qn in this case rather than this case. So in a nutshell, the greater the standard deviation, the more uncertainty there is in the measurement. We have defined the uncertainty in Q to be this expression. Let us now try to prove that this expression is exactly equal to the standard deviation in the outcomes. We know that psi n, the eigenvectors of Q, form a complete orthonormal basis of the vector space, because of which we can write any general vector psi as a superposition of the basis vectors. Operating with Q on both sides, we get and because Q is a linear operator, we can write this as now using the eigenvector equation, and because psi n is an eigenvector of Q, we can simplify this too. Similarly, we can also write subtracting this equation from this equation, we get let us try to interpret this equation. This is nothing but a scalar and this is the basis vector. So basically, these are the components of this vector along the basis vectors. If we take the norm squared of both sides, we know that the norm squared is simply the sum of the squares of the components along the basis vectors. So we can write this as Note that this term is simply the square of the uncertainty, and this term is the probability of getting the outcome Qn. So we can write this as this is exactly the expression of the variance of the outcomes. Hence, we get is nothing but the standard deviation of the possible outcomes. Now let us look at the uncertainty principle. So for two operators A and B, the uncertainty relation between them is given by this equation. I am not going to derive this equation here because it is not too difficult and I have written it in my report. However, I would want to present an intuitive explanation for what uncertainty principle really says. So if we have two operators A and B, then we say that they are compatible observables if they commute with each other, that is their commutator is equal to 0, and in the language of linear algebra we say that they are simultaneously diagonalizable, which means that if they are compatible observables, they have a common set of eigenvectors that forms a complete and orthonormal basis for the vector space. So the same eigenvectors both A and B will have. What this implies is that if A and B are compatible observables, then they will have a shared set of eigenvectors. So suppose psi n is a common eigenstate of both A and B. Then if the state of the system psi gets closer and closer to psi n, in that case the uncertainty in both A and B will drive to 0, that is delta A and delta B will simultaneously drive to 0. However, in case A and B are incompatible observables, then they won't have common eigenstates. So suppose psi n A is an eigenstate of A and psi n B is an eigenstate of B. In that case, if the state psi gets closer and closer to psi n A, it would get farther from psi n B, which means that if the uncertainty in A goes to 0, then there will be some uncertainty in B and vice versa. This is basically the uncertainty principle.